Hello. So in today's lecture, we're getting to the second major topic covered in a calculus course, namely integration. Before formally defining what integration is, or what the definite integral is, we need to motivate its definition. So the general idea here is that we're going to want to find the area of the region enclosed by the x-axis, the graph of some function, and the lines x equals a and x equals b. So a, b is just some closed interval. We have some function that there's some curve, some function there, and we want to find the area enclosed by the x-axis, these lines, and the graph of the function. Now, this, for a general function, this is actually somewhat complicated. However, for simple types of functions, we should be able to figure it out immediately just by using the definition of area, which is defined as height times length times width for a rectangle, right? So maybe I should just state that. So area in the plane is described maybe in the most simple form by the area of a rectangle. Right, and this is a really simple equation, right? So if you have a rectangle with a base and a height, or a width and a length, then we can have, which is base times height. Or maybe for convenience later, I'll just write it as height times base. It's the same thing. Height times base. Height times width, whatever. Maybe that'd be actually better, width. Sorry, I keep on changing this. I just wanted to match up later in the easiest way. So height times width. And so this is the easiest way to measure area. And if our function looks like this, we can't use a single rectangle to kind of measure it. But like, for example, if we had a function that looks like this, so here's like A, here's B, and our function is maybe constant. So maybe f of x equals to like 3, right? Then if we wanted to find the area underneath the curve there, right? And this is kind of easy, right? This is easy since the area is just going to be the height, which is just f of x, which is constant, times its width. Right? So it'd be 3 times whatever b minus a is, and that would be the area inscribed underneath that curve, enclosed by the x-axis in that curve, and the lines x is equal to a, x is equal to b. So this type of function we could do. Maybe, what are some other rectangle-like functions we could look at? Maybe something like a step function. Now this isn't continuous, obviously, but maybe, oh, let me say like this. Let me get rid of this one. I need it to be defined. Something like that. Now that's not a function, so let me try to kind of bend it a little bit. Okay, so that is a function. Now here, we could get pretty close to the area under this curve between, so it could be like this, right? This could be like A, this could be B. We could get really close to the area underneath this function. It is a function, there's a little bit of a slope there, by maybe cutting up the interval AB, we can partition it into two pieces. So those are our two pieces. And then we can look at this area here. I'll call this X1 right there. And then here we could maybe say, look at that area there. Notice that we get a little bit outside, but still that's kind of close, right? So we wouldn't have equals in this case. We'd have area as approximately, so it looks like the function, this is f, right? On this interval here, it's going to be whatever that is. So I would say maybe f of a times whatever the width of this is. So x1 minus a plus the height here that we made was f of b maybe. F of b times the width, whatever that width is, b minus x1. And so we have, so height times width, and with this picture here, we have some error. This is how much our error was for that procedure there. Okay, but notice that this function, even though it's not a square, it's square-like, and we were able to break up this function into two pieces, and we have some type of approximation to the area under that curve enclosed by the x-axis and the lines x equals a and x equals b. So what about things that aren't so block-like, right? Like, for example, like that is not a block. So maybe, or let's look at maybe something that's triangle-like. Instead of moving to something complicated like that, triangles are kind of like rectangles, right? So let's look at maybe a triangle type area that would be enclosed. And again, we're going to keep on using this simple notion of rectangles as the easiest way to calculate area. So let's look at maybe, so suppose we want to approximate the area of the region line between, say, so I want some type of triangle, so maybe f of x equals x plus 1, and the x-axis and the lines x equals -1 and x equals 3. I know 2. Make it simple. Okay. So what does this function look like? That's a bad Cartesian plane. We draw a better one. This is not too much better, but maybe. Okay, so then draw my tick marks here. So this graph looks like this. So there's the graph of our function, and we want to know the area enclosed by from -1 to 2. That area. Now we can find out the area of this without using a rectangle. Right? The area of a triangle is 1/2 base times height, right? So what's the base? 1, 2, 3. What's the height? 1, 2, 3. So we know the answer. We know the answer ahead of time. And yes, we kind of did use a rectangle because the formula of a triangle, the formula of the area of a triangle is derived from a rectangle because the triangle is exactly half of a rectangle. But let's see if we can use the areas of rectangles without having to like scale them to fit this exact picture. And by that, I mean, I want to use actual rectangles and not use that triangle. So I guess I'll have to show you. All right, so here's the graph of f again, okay? So one way that we can approximate this area that we know to be 9/2, right, is to say maybe if we, so this is the interval in question. So I'm going to say that this is x0, this is x1, this is x2, and this is x3. So basically what I've done is broken up the interval from -1 to 2 into these pieces. So basically x0 is equal to -1, which is less than x1, which in this case is equal to 0, which is less than x2, which in this case is equal to 1, which is less than x3, which in this case is equal to 2. So this is a partition of this interval here. So this is a partition. And I'm going to denote it by this triangle symbol. So this is, again, a partition. Right? So a partition is simply just taking the interval in question and then breaking it into its pieces. So now that we've done that, I'm going to make a bunch of, well, I'm going to make 4 rectangles. Okay. Oh, no, sorry, 3 rectangles. Like that. So notice here the height of the rectangle is, so that's like f at x3. The height of the second one is f of x2. The height of this third one is f of x1. Basically, the height in this case here of each of the rectangles corresponds to the highest value of the function in that subinterval. So these are like little subintervals that we've made. We've made 3 of them actually. Okay. So the height in this case is going to be, for all of these, that's going to be f of what I call capital M I, which is the largest value for f on the ith interval. So if I just choose the heights of my rectangles to be the tallest point, it happens to be the case that it's going to have this shape. Now, in order to approximate the true area, I can just take that area and add it with this area, and then add it with this area. And of course, there is error here. Like that's error, that's error, and then here's error. But still, we have some approximation by doing it. So what is this approximation? Well, it's going to be I'm going to denote this by S with a capital with a bar above it to mean that on each of the intervals, we're taking the maximum value. So what we're going to do is we're going to sum from I is equal 1 to n f mi times the width of these partitions, right? So we have width, height, width, height, width, height for each of these rectangles, right? So I'm going to denote that by change in xi, delta I. So here, that is simply xi minus 1. Right, so what's the width here? It's x3 minus x2. What's the width there? It's x2 minus x1. What's the width there? It's x1 minus x0. So that's just the width. And this is the maximum value. So max f on the interval xi minus 1 to xi. So that's what we're just taking that to be the maximum. Okay. So what is it in this case? Well, It just so happens that I picked the widths of each of these subintervals to be 1. That 2 minus 1 is 1, 1 minus 0 is 1, 0 minus -1 is 1. Each of these have width 1, so it makes it pretty easy. So then, what is this sum? It's just that times 1, that times 1. Again, I picked it for convenience. So what's f of x3? So it's going to be 3 times 1. So 3 times 1, and then x2 is 1, so it'd be 2 times 1. And then finally, 1 times 1. So we get 3, 5, 6. Now, it's not the answer, right? That's the answer. But it's still some type of approximation, right? It is close, sort of. It's better than just taking a random guess, obviously, right? So what about if we refined the rectangles a little bit more? Okay. What if we refined them? What if we made more of them, right? Or what if we, instead of picking the maximum on the intervals, take the minimum? Let's look at that. Same picture. And I'm going to partition, I'm going to take the same partition I did over here. So this would be x0, x1, x2, x3. So -1, 0, 1, 2. And so here are my intervals. There's there, and then there. So on that interval, instead of taking the maximum like we did here, I'm going to take the minimum. So the minimum value for the function on this interval looks like it's right there. So that'll be the height for our rectangle. And then the minimum value on this interval is going to be here. That height. And then the min here is just there. So here is what we would calculate if we added the area of these rectangles. And then here, this is the error. All this is error. We're missing that, right? So here, this is like f of x2, f of x1. That's f of x 0 would be the height of that rectangle. So here, these are going to be denoted by little n. And these are the minimum value. And the ith interval. Okay, so now this is different, right? This was maximum, so now we just replace it by minimum and we have a different sum. For that given partition, we're using the same partition that we made, right? This is going to be the sum. Y is equal 1 to n of now the minimum value on the ith interval times the width of the interval, which it happens to be the case that in this partition, the widths of each of the intervals are the same. And I picked it in such a way that it was easy for us to use. The widths are always going to be 1. So what is this sum? This is the height here would be f of x2, so 2 times 1 plus 1 times 1 plus 0 times 1. That's the height of the last rectangle. So now we have 3. So again, what we can argue, we actually really need to prove it. Is that at least if we have continuous functions, for sure, that the upper sum is always greater than or equal to the area under the curve and above the x-axis inscribed by A and B. And then the lower sum is always less than or equal to that area. But still, it's kind of annoying that we still aren't at 9/2, right? So maybe we should we should refine our partition to make the interval smaller, right? Because if you think about it, if we just would have used one rectangle, we would have had a big old chunk of area there. If we use 2 rectangles, we would do worse than if we did 3. If we use 4 rectangles, we'd do better. If we use 5 rectangles, we'd do better. If we use 6 rectangles, we do better. In fact, maybe we can come up with a formula for both the upper sum and the lower sum for this function in terms of the number of intervals, right? How we can refine our partition to more and more pieces, which gives us more intervals, which gives us more rectangles. Maybe we can see what these sums equal, right? So let's take a look at that. And we're going to focus on that and that. And we're going to see what happens as we take more and more intervals. Or we partition it into more and more subintervals. Okay. So one thing to note, so if we were choosing each of the intervals to have the same length, right, then what we can say, so if we choose the partition to have the same length, we can say that the change in x is going to be equal to b over a, b minus a over 2. Or no, not over 2. That would put it in 2 pieces. Like that. Okay, so then our partition would be, so not our partition, but our change in x, if we choose it to be equal throughout and equal to this. So what is A? A is -1, B is 2. So we have 2 minus -1 over n. Okay. So depending on n, if we choose n to be 2, then they would each have, there'd be 2 partitions of length 3/2. If we choose n to be 3, there'd be 3 partitions of width 1, which is like we had. If we have n is equal to 4, there'd be 4 partitions of length 3/4. Okay. I might have said that last one wrong, but this is the width of each partition. So if that's the width of each partition, then I can say that A is equal to x0, which is less than x1. Well, I'm going to write it a different way. So this will make sense after the fact. So I have x naught equal to a plus 0 times my change in x, which is less than a plus 1 times my change in x, which is less than a plus 2 times my change in x, which is less than dot 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 less than a plus n times my change in x. And that's going to be equal to xn. And this is like x1. Oh no, sorry. Maybe I'll write it like this. This is x naught, which notice is the same thing as a. And this is x1. This would be x2. Dot, 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 dot. This would be xn. And notice that that's equal to b. Because what is the change in x? It's b minus a over n. So n times that is just b minus a plus b minus a, it evaluates to b. So if I choose my partition to have equal widths, then this is what the numbers will look like, x0, x1, x2. So these are my now intervals. Okay. Now, with this function here, it's strictly increasing, right? So we should be able to figure out, since it's strictly increasing, we should be able to figure out what our little mi is and what our big mi is, right? So in particular, if we're looking at the interval xi minus 1 to xi, then this would give us little mi that's equal to f of the left endpoint. So maybe I'll do it over here. There. And then here, this would be your big mi. Why? Because it's strictly increasing, I know that if I partition it, the left-hand side is always going to be the smallest value of the function, and the right-hand side will be the largest. It's just as convenient. So we know for each of these, it's going to be the left or right endpoints. Okay, so we know that the upper sum for this partition is equal to the sum y is equal 1 to n. Okay, so it'll be for each of these intervals, it's going to be f of xi times the change in x. Okay. But actually, we know what the change in x is. The change in x is 3 over n. In the lower sum, so for given interval here, it's going to be the left endpoint. So x of I minus 1 times the change in x, the change in x is this. Okay. All right. So we're getting somewhere. Okay, so what can we say about f of xi? Well, f of xi, so what is xi is equal to a plus I times the change in x. And the change in x is just 3 over n. It's like I times 3 over n. But what is, we just have to plug that into that. Okay, so this equals a plus I3 over n plus 1. There's a plus 1 there. Like something looks off. Let me see. What looks off here? No, I think that's fine, actually. So this is what it is. F of xi is equal to that. So all times that. A plus 3i over n plus 1. Yeah, y'all can read that. Right. Okay, so what about that? What's f of I minus 1? Well, so f of xi minus 1 is just f of a plus I minus 1 times your change in x. So you just take that, you plug it in there. Well, your change in x is 3 over 8. So if we plug that in, we get the sum is equal 1 to n of a plus I minus 1 times 3 over n plus the 1 times 3 over n. Okay, so it looks complicated, but we're like, what's happening? So the upper sum for that partition is all of that pixels. So a plus 3i n plus 1 times 3 over n. Okay, so let's distribute this in. So what do we get? Well, actually, this sum here is only working on these indices I, right? So that 3 over n can just be brought out. Because there's no I in that term, it's just a number multiplying the sum. Okay, and in fact, we can split this sum up. That is equal to 1 to n of that. Okay. Plus that. I just split the sum up. It's that, what's that, what's that, so I can split it up however I want. I just decided to look at this sum on its own, and then look at this sum on its own. So, oh, that shouldn't be, it's 3 over n, right? Times I. So I can take out the 3 over n, and I have the I on the inside. Okay, so what does this become? 3 over n times, so this sum, there's no I, so you're just adding that n times. So it's times n times a plus 1. Plus 3 over n times n plus 1 over 2. Now you might be asking yourself, where did that come from? Well, it turns out that if you sum the first n integers, it's equal to n times n plus 1 over 2. So that sum is equal to that. That's, I wouldn't expect you to know that unless you read through the very introductory section on summation notation. So that is what the upper sum equals. How does this help us? Well, I need to simplify it one more time. Distribute that in. Oh. I could have made this a lot easier. What is A? A is -1. So -1 and 1, that goes away. So then that times that. Times that. So what is that? That's going to be, so that's 0. 3n times 3n is 9n squared times this, so it's going to be 9/2 of n plus 1 over n. That times that times that is that. Right? Because you get 9n squared, n over n squared, just leaves you with n, so you 9 times n plus 1 over 2 times n. Okay, well, what does that mean, right? Like, what's going on here? All we know is that the upper sum for a partition with equal lengths on that function from -1 to 2, all we know is that it's equal to this. Right? But what do we know about n, right? N is the length of each interval, right? So what can we say, right? And that n isn't the length of each interval, n determines the length of each interval, right? If n is really, really big, then the width of each interval, sorry, the width of each interval, if n is really big, is going to be really, really small. So in this case, if we make the norm or the length of the maximum intervals, right? If we make this length, right? If we make that length go to 0, this is like equivalent to saying we want n to go to infinity, right? If we want these all as a whole, we want each of them to go to 0. That's equivalent to saying taking n to infinity, right? Well, what happens when we look at that limit here? So if we look at the limit as the length of the maximum interval goes to 0 of the upper sum, that's like taking n to infinity here. What is that limit? The limit as n goes to infinity of this is 9/2. And what did we know about this? This has height 3, width 3. So the area of that triangle is 3 times 3 over 2, or 9/2. So even though we didn't invoke anything other than rectangles, if we make infinitely many, or if we make the intervals infinitely close together for that limit tends towards the answer, the actual answer for this. And it turns out if you work it out for this sum, it also converges to 9/2. So A again is -1. That's the left-hand side, right? So that -1 and that 1 go away. So it's that times that times that. And if you use that formula again, but replace that with an n-1, you'll get the same limiting value. Okay. So in fact, if your function is continuous, then this will provide the area enclosed by x equals a, x equals b, the graph of the function, and the x-axis. I might as well show you what that equals. So again, a is -1, that's a 1, so those go away. So the lower sum here is going to be that plus that is 0, and then 3 over n times that. Like that. Again, you can take that out because there's no I there. Like that. So this is like summing from 0 to n-1. If you plugged in I equals 1, you'd have 0, I equals 2, you'd have 1, so forth and so on. So this is like summing to n-1. You can adjust the indices, right? Hopefully you see that this sum is like summing from 0 to n-1. Or in other words, I equals 1 to n-1 I. So then you just plug in this formula and replace n by n-1, so you'll have n minus 1 plus 1 is n minus 1 there. So this would be so you get 9/2 times n minus 1 over n. And where does that go? As n goes to infinity, 9/2. So the upper sums converge and the lower sums converge to the same thing. And actually, in that case, we say that the function is Riemann integrable when these upper and lower sums converge to the same number. Okay, so this is kind of a long-winded explanation of what's happening. When we were calculating areas using these things called definite integrals, when we were doing that in the following lectures, in the background, we have to always remind ourselves that we are really taking limits of these sums, upper and lower sums, or Riemann sums, which we will discuss more in my next video lecture. So I'll go ahead and stop it there.